It's an immense pleasure for me to welcome you to this special colloquium inserted in the webinar series of the graduate program in physics of the Federal University of Pará in Amazonia, Brazil. I ask everyone to kindly leave the microphones and cameras turned off, except for the moment you're going to speak. Questions will be allowed in the end, unless otherwise requested by the speaker. The questions can be made using the chat. If you want, you can write it down in Portuguese and I can translate it to English. Well, today we are very much honored to listen to Professor Carl Edwin Wieman, who is a fellow in the US National Academy of Science and in the Optical Society. Professor Wyman has never visited our graduate program in Amazonia or any institution in Brazil, so that today is a very special occasion for us Brazilians. Professor Wyman received his Bachelor in Science in Physics from MIT and received his PhD in Physics from Stanford University, where his doctoral advisor was Theodore Hansch. Professor Wyman is a professor of physics and education at Stanford University. Professor Carl Wyman has done extensive experimental research in atomic physics and university science and engineering education. For his achievements, Professor Wyman received the E.O. Lawrence Award in 1993, the King Faisal International Prize in Science in 1997, the Lawrence Medal in 1998, the Benjamin Franklin Medal in 2000, the Nobel Prize in Physics in 2001, has been appointed as the Carnegie Foundation Professor of the Year of 2004, and received the Orsted Medal in 2007. Professor Wyman founded the Physics Education Technology, the PhET project, now expanded to other disciplines, which provides online interactive simulations that are used over 100 million times per year to learn science, and recently published the book, Improving How Universities Teach Science. He is currently studying expertise and problem solving in science and engineering disciplines, and how this can be better measured and taught. What is related to the theme of the special colloquium he will be giving for us today, and I should not keep you waiting longer for that. Professor Wyman, thank you once again very much for having accepted our invitation. The audience is yours.
Okay, thank you. It's a pleasure to be speaking here, to reach out across Brazil in this way. So I'm going to say that just because the limitations of the virtual speaking, probably work best not to try and interrupt during the talk, but I'll be happy to stay for a long time afterwards to answer questions and discussion on this. So what I'm going to cover is first just a basic introduction on kind of the educational goals of physics education and some of the research-based principles of learning, and then talk and give about applying these principles in university courses in physics and measuring the results. This is the research side. And then I'm going to finish with really giving you a summary of what research tells us broadly about teaching expertise for university physics. What's the most effective at getting students to think like physicists? Now, before I do, though, I want to sort of explain my perspective on this, a little bit of how I got into working in education in this way. And it really came about because of my atomic physics research program and being puzzled at this consistent pattern that I saw, which is these graduate students would come into my physics lab having done wonderfully in many years of math and science physics classes, but really didn't seem to know how to do physics much at all. But it was clearly not something defective fundamentally in them, because after just a couple of years working in the physics lab, they had turned into expert physicists. And so after I saw this happen enough times, I decided there was a real fundamental question here about learning and physics expertise. And so I tackled that just like I would, a physics problem of digging into the research on what we knew about how people learn, particularly how they learn physics, to try and make sense of this. And after 2 or 3 years of reading lots of research papers, I could understand enough to see that this made complete sense, actually. It explained the puzzle. It also made me realize there were a lot more effective ways to teach physics than what was in the mostly in practice. And it also got me started in doing physics education research, doing experiments, collecting data, looking for fundamental principles. So not so different from actually doing other kinds of physics research. And so for 20 years, I actually had 2 research groups, one doing blasting atoms with lasers and the other studying how students teach, think and learn and how to teach to physics. Now, but I've always had the focus really of this from the very beginning is shaped by what I label as expertise. Namely, how does one think like a physicist in solving problems? And so when I'm talking about that work, sort of keep that in mind as the fundamental goal of I'm looking at is having people learn to use the methods and knowledge of science, of physics, to solve problems, to make decisions like a good physicist would in relevant situations. Now, just in the past couple of decades, there's actually been quite a lot of progress from 3 different fields that have given us a much more complete and complementary picture supporting this idea of how how people learn complex thinking like a physicist. And it comes from the combination of cognitive psychologists who study the basic properties of how the brain thinks and learns, more recently brain research looking in more details of what's happening in the brain, and then people like myself, faculty in science and engineering departments at the university level, doing experiments and studies in classrooms on different ways to teach and measuring different amounts of learning. And so, I'm going to touch on that, but I'm going to start by just giving you the most basic summary of what we've learned, which is to completely rethink really how this kind of learning takes place. And the old model that people thought, which frankly is still in practice in most universities, is that these brains come into our classrooms and they vary in different ways. And then we immerse those brains in knowledge through our curriculum, and it soaks in to different amounts, and that amount depends primarily on the properties of that brain. And so with this paradigm of thinking about learning, the focus of most universities has been two things. One is, what's the content of this soup we're going to immerse it in, namely, the curriculum, what topics we teach in what order and so on. And then also selecting the best brains to admit to our universities, the ones that it'll soak into best. Now, it turns out that's just a fundamentally wrong model for thinking about learning. And what the modern research has shown us is really these brains come into the classroom not all that different, but highly changeable, actually. And the educational process really transforms those brains, rewires the neurons in there. And it's really within this rewired neuron connections that you have improved capabilities. So rather than trying to put knowledge into brains, you're really trying to transform those brains into being better, more effective, more knowledgeable. And with modern brain imaging, we can actually see this happening, or the researcher looking at it can. And so this is just an example here of two people in an fMRI machine while they're interpreting medical X-ray images. And on the right, you see the brain of a medical student who's just learning how to do this. On the left, you see an expert radiologist who's had many years of training at this, and you see their brains are really they're activated and used in completely different ways between these two. And some studies have even been able to show during the learning progression how the brain imaging is actually changing. So with this paradigm of teaching, the focus then of those who been looking at this and studying it is not on selecting the best brains, but rather what's the most effective teaching methods that are the most effective at transforming these brains to have the higher capabilities. Okay, so I'm going to now move into much more detailed discussion of these things, looking at the basic principles of learning and courses the research has shown, and measuring some of the results. The basics that underlie almost all of the good research in, not just in physics, although physics has kind of led the way in this. Other sciences, biology, chemistry, now earth sciences are doing similar sorts of things, and that they're really based around, first you decide how you make good measurements and figure out what you want to measure that really matters. And it really comes down to testing how well the students are learning to make decisions like experts in relevant real-world contexts that student who's studying physics or biology might situation they might be where you want them to be able to make decisions. And then once you have a good develop good tests of that, then you compare the results for different students who are taught using different teaching methods. And most of the work for many years, just because the predominant way of teaching at universities is lecture, is to compare the lecture approach, which is basically telling students, if you're in a situation like this, this is the answer. This is what you should be doing to solve problems. And the alternative, which is really the sort of the research-based approach, sometimes you might have heard the term active learning, is to have the students actually practicing as part of the educational process, practicing making decisions in particular scenarios that have been created. And they don't just practice that, but they also need to get fairly immediate feedback on how well they're doing so they can change that. And so you can think about, the project B is really, it's exercising the brain. And it's because the brain requires that kind of activity and exercise really to make these changes in neuron connections that I've claimed is really where learning lies. So here's an example of how this is done, and a research measuring the effect in a large classroom or a large class. So this was an experiment I had some involvement with, and so it looked at the very large introductory university physics course at British Columbia that's taken by all the students who are going into engineering. So it actually had multiple sections of 270 students each. So we were able to pick 2 sections, which by a whole bunch of different tests looked just completely identical. And then we taught those 2 sections in 2 different ways. The control section was one taught by a highly experienced professor, had good student ratings, but used the standard lecture approach. And then the experimental class was someone who was a fairly new PhD, but had been trained in program I ran in these principles and methods of research-based teaching. And so the 2 instructors agreed to cover exactly the same material and the same amount of class time, 1 week of lectures or 1 week of class time. And then they had a test on this material that the students were given as a surprise just at the start of the next class. So this was not to look at the kind of learning you get from an entire course where students are doing homework, studying for exams, and so on. This was a research study to look at, okay, what's the learning they're getting just during the classroom experience. There's other studies that look at more broadly, and I can talk about that. So what happens in the experimental class? Well, this is very similar to many other similar studies in basic design. The students have a short assignment ahead of class where they just get basic information, terminology. And then during class, rather than being told information by the faculty member, they're being given questions. And so the class starts with a question like this, where the students are shown this circuit with light bulbs and a battery here, and they're asked, okay, when this switch is closed, what's going to happen to the brightness of that battery? Now, every student in the class has to individually answer, and this is done using some technology. When this study was done, it was used clickers. Now most people have replaced that with mobile phones to do the same thing. But basically, the student has to decide which of these answers they think is right. They push the button on their phone or clicker. The instructor has a receiver, and so it records what their name was and what answer they chose. And then they're not told the answer or seen what the votes are. They're told they have to discuss with their neighbors. So this is a big classroom, 270 students, but they all, little groups of 2 or 3 throughout in the classroom discussing what the answer was, and then they have to re-vote. And while they're having these discussions, the instructor's circulating up and down the aisles, listening in on those conversations between students to get little snapshots of what's going in their minds. How are they thinking about this problem? Both what aspect's correct and what's incorrect. And then after they re-voted, then they'll see the results. They'll demonstrate what actually happens with the light bulbs, and the instructor will then do a follow-up summary, giving feedback on which models the students were using of electricity, were correct and which were incorrect. And what's really important from a cognitive standpoint of giving feedback on which ideas were incorrect and why. It turns out that if you just tell somebody, oh, you're wrong, here's the right answer, people don't actually learn very much from that. What they learn from is when they say, okay, you're incorrect, and here's how the reasoning you used was incorrect, and here's how you need to change it. That's when actual learning takes place. Now, this was a very basic conceptual question. For more mathematical topics in this class and many others, they'll have things where they have to write out more on paper and so on. You have different ways of collecting that. So if you think about this, you can see how students are practicing thinking like physicists, making decisions like a physicist would. They're having to formulate and decide on a conceptual model of how electricity works. They're having to test that out into predictions it would make in this case and other situations they know about. They're having to critique their reasoning and the reasoning of others by evaluating this. So these are all very much how physicists spend their time thinking, but it's just mapped that onto a situation that's suitable for these students at their level. Now, equally important to the idea they're practicing thinking here, they're also getting feedback, and they're getting that from on their thinking. They're getting from the other students in their discussion. They're comparing their prediction to the demonstration, and they're getting it from the instructor who been listening in and seeing how they're voting is vastly more informed about their thinking than in a typical lecture class. And so this combination of practice and feedback is really what makes a difference. Okay, so like I said, this was part of the experiment. This is just talking about the teaching methods. And so does this work? Well, as I said, they were both sections given a surprise quiz after the end of this week of classes. Here's the histogram showing the scores on this quiz versus the number of students here. And you can see a profound difference. This is the distribution in the standard lecture, and this is for the experimental section. Now, on this particular test, random guessing would give students about 3, and so really the amount they learned is how much above 3 they are. You can see that the learning from lecture was really tiny, and if, I've tried it in my own lectures and many other things, and it's really striking how reproducible this is. You could do the experiment yourself. So both how little the small amount of learning was from lecture, but also emphasize the point that you can see that this way of teaching wasn't just more effective for any, the top or bottom students. This is clearly an improvement for the entire student population. The whole distribution has moved up, and that's just because this is how the human brain learns, and all these students have brains. I could give you many more examples, but I won't take time for that. I'll just say we've got lots of other comparisons. Here's using the same kind of teaching methods that I illustrated, same kind of questions and discussion in class, but actually looking at the results of an entire course, or in this case, 4 courses in computer science. And here they looked at the drop in failure rates from the class, and basically for all these different instructors. So you have 4 instructors just change their teaching methods. And so on average, for these core computer science courses, they're now getting about 1/3 the failure rates they had before. This is for the University of California, San Diego, so it's a very large public university. This is a lot of students who are benefiting just because the instructors change from traditional lecture to these better research-based methods. Now, there's been lots and lots of work on introductory courses, particularly introductory physics courses. And it's only been relatively recently, and my own group has been sort of the lead of this, of applying these basic principles and testing them in more advanced physics courses. And this reference here gives one study that basically will tell you about the details of design and implementation and show the substantial impacts and improvements in learning. I'll just point out that now at Stanford, we have in the courses taken by the physics majors in the 2nd through 4th year, now 8 of these courses have been transformed, and with very high student approval and and better participation in learning. There's examples of applying these ideas with good results all the way up in Cornell University, now teaching the graduate quantum field theory, this following with these same basic principles. And just to give you a little better idea of how this works in these smaller, more advanced classes of the type illustrated in those pictures, is that the underlying principle is still the same, that students have to do some modest preparation before they come to class. Instructor introduces the ideas, and then most of the time is spent with the students working on some activities in these advanced physics classes. These are worksheets they have to fill out individually, but they work together to understand them. And, these can be a lot of mathematical calculations and justifications, etc. But they work through this, for typically one part for 10 minutes or so, while the instructor is sort of monitoring how people are doing. And then the instructor will then spend some time giving feedback on their work, answering questions, making sure everybody knows how to do it, and so on. And I want to emphasize, in both the experimental class I talked about before and in these kind of examples, it's not that the instructor isn't doing anything. They're actually spending quite a lot of time, the majority of class time, giving feedback to students, answering questions, and so on. What they aren't doing is just giving information out to students who kind of aren't prepared to learn from it. What they're doing is responding and guiding and giving feedback, and really playing an absolutely critical role in the learning process. And so, just to emphasize, the two essential features in all of these things are the students are actively thinking, they're practicing expert reasoning, and they're having to think intently to do it. That's really what's changing the neuron connections to make them more expert-like. And the instructors are now much more knowledgeable about their thinking, giving more effective guidance and feedback on that. So I just give you a few examples. There's although it's surprisingly not still widely known around the world, there's about 1,000 research studies that I was able to find where they did these comparisons, like I illustrated, of the traditional lecture method with the active learning or research-based teaching methods. And the first thing that's important to recognize is that this really dominates the teaching methods really dominate the learning results. It's not, whether the teacher is outgoing and enthusiastic and lovable or not. It's really what teaching methods do they use that has the students, what kind of thinking the students have to do. But this research-based teaching consistently shows greater learning and lower dropout and failure rates. So the rest of my time, I'm really going to focus on essentially take-home lessons. What does the research say that produces the most learning that you should be including in any teaching you're doing, basically, to make it more effective? And so it's really illustrated with this figure here, that in the middle here is what the students really have to be doing. They're learning by practicing making decisions like an expert would, with good feedback. And the good feedback here means it has to be timely, specific, and actionable. So students have to get that feedback while they're still, aware of how they're thinking about it. And it's got to tell them that they either continue thinking like that, or most critically, how they can make that thinking better. And so that's kind of the key part of the practicing with good feedback. but then there's a whole lot that goes into the designing of the educational activities. That's, what are they carrying through that's making the best practice. And those are kind of all the things here: disciplinary expertise, taking into account the knowledge and experience of the students, so these things are matched appropriately, and building on that past knowledge, taking into account motivation, making the student really eager and anxious to work hard to master that learning, which is really critical. And there's some basic issues about how the brain works that you need to take into account here. And then particular issues about implementation. So I could spend, we have research on a lot of these different things, and I could spend a whole lot of time. I'm just going to touch on a few of them a little bit to give you some ideas you may not be aware of. As I said, these things really define expertise by showing what practices the research now consistently show more learning than if you don't have those. So the disciplinary expertise is really a critical one, and it's really the justification, I think, for research universities for having, people teach physics who know physics, have done, PhDs and gotten research in it. It's really very critical that those go into defining the tasks, the decisions that have students make that really represent the thinking in the discipline. And this is an area where my group has been doing a lot of research lately, of actually looking at what this thinking and decisions make by experts, typical, faculty member at good high-level universities, and in scientists and engineers, in experienced at good companies. We've also even looked at medicine too, and as we study the expert problem solving of authentic problems, not the kind of things you find in the textbook or an exam, but real problems that people are doing in their job, the kind of problems you'd like to train your students so they can go out in the workforce and be good at. And we find that all of these things involve making decisions with limited information and solving a complex, authentic problem. Remarkably, it's the same set of 29 decisions that occur here consistently across all of these different fields and all kinds of problems. Now, although the decisions are the same, how they make the decisions, that requires lots of very specialized, unique knowledge for that discipline. So let me just talk about this from the point of view of what you want to build into your educational activities, of the kinds of decisions that students need to be practicing making. And I'm going to give you examples that apply almost across all science and engineering, but they definitely are particularly focused on physics. So given a problem to solve, what concepts, the first thing, decide what concepts and models are relevant to that problem, conservation of energy, momentum, Ohm's law, etc. Decide what information is relevant and what irrelevant and needed to solve the problem. What approximations or simplifications are appropriate, how you can justify them. And then deciding on what potential solution methods make sense to pursue. And then there's another 25 more, I think, until one gets down to, once you have a solution, then there's deciding thinking of does this make sense, and does it pass all the tests that I know and that the discipline has for a good solution of such a problem. Now, I list these in particular because if you look at these, I think any physicist would look at these and say, sure, when I go to solve a real physics problem, I go through exactly these things. But if you look at these, you also can think about, if you look at the typical, textbook or exam problem, all these decisions that I've listed, they've been removed from the problem, right? You have, it's a chapter 3 problem. Chapter 3 is conservation of energy, so they don't have to think about that. All the information and only the information needed is given in the problem. If there's approximations they're supposed to make, they're always told, either you should ignore, you should ignore friction or air resistance, etc. And at the end, you're just supposed to produce a numbers, that part of the solution that isn't to think about how you could justify this solution, making, arguments for whether it makes sense in the real world, etc. And so what I emphasize is this actually goes way back to the original thing of when I was wondering about how come these graduate students could do well in courses but not do physics. It's because these courses were having them solve problems, make decisions without actually learning how to solve real physics problems and real physics decisions. And so this is a pattern that we see in we researchers see over and over again, of students will learn knowledge and be able to show that on the traditional tests, but they don't really know how to use that knowledge in any meaningful way. Okay, I'm going to just now cover a few other things quickly that you may not be familiar with, but there's the ones in here, the prior knowledge and motivation, those are kind of reasonably obvious to anybody who's taught. Brain constraints aren't so much. One of the most important ones is to understand how the memory works. So a basic but reasonably accurate view of the memory is that, okay, there's the long-term memory, in here. And this is what most of us think about memory. It's got this enormous capacity, and it can remember things for a very long time, years, decades, etc. But then there's another aspect of called the short-term working memory. And this is really a buffer between the information and ideas that are coming into the person's brain and the long-term memory. And this buffer, it works on, short time scales, minutes, so on. So it's really relevant to what happens in the classroom. And it's, you can think of it as really what people can pay attention to. And so that has this tiny capacity of typically sort of normal brain, sort of 5 to 7 things that you can think about it, they can keep track of and remember, or just think what they can pay attention to. And so it turns out that when you hear or see some new thing, it actually, this short-term buffer is pretty full. And so some new thing comes in, it pushes things out, and they never can get into the long-term memory here, which is what you really want. And so this constraint of working memory is really important when you're thinking about teaching students in something like a classroom, because every additional item doesn't just mean they won't learn it. It actually can displace things you care about. And so lots and lots of studies showing how putting new items in reduces the processing and learning that students can do. And so some of the things that do that is split attention. If students are splitting their attention between listening to, class or lecture or other students versus checking their phones, looking at email and so on, that if you measure learning under the case, it's just a disaster. It just drops precipitously. But there's other things instructors do that they don't realize make a big difference too. Use of jargon. If they're not really familiar with it, it fills up that buffer and blocks anything else they're going to learn. Showing fancy, nice pictures, picking at attractive things just to kind of show attention and look nice. Turns out if they pay attention to that, they're going to be learning less. Even these little interesting little digressions or jokes actually hurt. And both instructors and students get sort of outraged when I say this. And they say, because say, oh, that's the only time students were paying attention to me, or students, oh, that was the only thing that was interesting in that class. And that's exactly the point. If people are paying attention to something because of the limits on how limited the short-term working memory is, paying attention to that means, yes, they'll be remembering that joke, but that means it'll displace some of the material that you actually want them to learn. There's also some basic constraints about long-term memory. I'll just try and go through this very quickly. At some level, it's not trivial, but you can get stuff into long-term memory, but there's a big problem with recalling it. And it's because new learning interferes with recalling of what people have already learned. And so this really goes against our concept and practice in teaching of covering chapter 1 and figure, okay, they mastered chapter 1, I go on to chapter 2 and chapter 3 and so on. I don't have to worry about chapter 1 anymore. But it turns out that's not the way the brain works. Learning more things puts in interference of neuron connections there that actually reduce the original learning, or at least the recall of that learning of chapter 1. And so you really have to have repeated recall, briefly, but something where they have to think back about the ideas in chapter 1 as they're learning chapter 2 and 3 and 4, if you want to have good long-term memory and recall of that information. It doesn't work to think it's learned once, it's done, and then it's going to be settled. Say quickly, just a couple of final things about implementation. These things up here are all what goes into the design of those activities, implementing it in class. We've also lots of research on that. You have to design good tasks, but they have to have deliverables. The students actually have to be doing something, answering some questions, filling out worksheets, etc. Another aspect that people find is helps in a variety of ways, but it's this working in groups, and there's some basic principles basically behind that often aren't understood and aren't recognized. So I just want to say a little about this, because a lot of instructors, the students will work through some problem. Instructors just can't understand how talking to fellow students about this they could learn more than hearing their expert instructor actually explain the solutions to them. But the research, and we've got some good data showing that actually this is very true, that talking to your fellow students learn more. And there's actually a very basic, and it's this very interesting area in cognitive psychology. There's a very basic cognitive process that goes on here, which is that being able to show that when people are explaining something to somebody else, or even thinking they're going to have to explain it to something else, it actually triggers a unique and different cognitive processing than if they're just sitting there trying to figure it out by themselves. And so this kind of kicking in this interaction with other people and mastering it brings some more cognitive power here that produces more learning. It's also extremely useful for the teacher to be listening in on these student conversations to kind of guide their instruction. And so that's two big benefits to this having group work in class. Okay, so I'll just wrap up here then, so we have time for questions. I just covered it, skipped over it, but I tried to give you an idea of the basic summary from lots of research that really shows not just how to achieve better learning in science courses than our traditional teaching methods of lectures and so on, but we also now understand the principles of why these things work, really almost down to the level of what's going on in detail in the brain. Okay, so I'm sure that many of you are thinking this, because whenever I give this talk, I always get a question like this afterwards of, someone saying, but you're saying traditional lectures can't be as bad as you claim, because, look at me, I'm a university professor. I was taught by traditional lecturers, and look at how well I turned out. And the point here is that, this was actually exactly the same logic and justification for use of bloodletting in medical treatment. And so that's why it remained the treatment of choice for 2,000 years, because of the same failed logic. And if you really want to look at take a scientific approach to teaching and learning, you have to have a proper comparison group. It's not enough to say, well, I got to this point by listening to lectures, but to see how much better you could have done if you'd been taught by a different approach, or more importantly, how much better so many other students who weren't as successful would have been more successful if taught differently. Okay, so with that, I'll just stop. Here's some of my favorite references if you want to learn more about this, but the general ideas and particularly specific details about implementing things at this website here. Also, I recognize that I've covered way more things than fit in your short-term working memory, so I'll make sure my slides are available and can be distributed so you can go through those. So with that, I'll stop and guess I'll get questions relayed through Luis.
Okay, so thank you very much, Professor Wyman. At this time, I will ask everybody to turn on their microphones to acknowledge your excellent talk by clapping our hands for you to see us. Well, I would tell again that if you have a question, please register in the chat, either by writing down your question. It can be in English or in Portuguese so that I can translate, or you can simply, if you want to make the question yourself, just write down, I have a question, and at the time of your number in the registration, I'll let you know for you to make the question yourself. While people is writing down their questions, let me just give you some further information about. So we had most of the time more than 120 participants from almost every side of Brazil, from north region where we are, from the south region in Rio Grande do Sul, that's like 5,000 kilometers away from where we are now, in the northeast, in the southeast. So we also have people from abroad, like people from Portugal and people from Iran. And by saying that, I mean, we have people not only from America, but we have people from Europe, and we have people from Asia also, right? So it's really amazing, right? I have to register also the presence of our faculty members, of our professors and teachers of our undergrad and graduate programs, our students here from Amazonia, but also from all around Brazil. Okay, by having said that, I will start with the question, So the first question I have is from Professor Jorge Simões de Sá Martins. Before that, I shall tell you that Professor Sá Martins has left in YouTube many of his lectures. And I can say that he's one of the most popular teachers in Brazil and having really excellent classes all around. So this changed a bit my mind about the effectiveness of these online lectures. But anyway, Professor Sammartins, do you want me to read your questions or do you want to make it yourself?
I can do it. Actually, I met Professor Wyman. He probably doesn't remember me, but I was in his Nobel Prize celebration at Boulder. Back then, I was a researcher at the C4 lab with Professor John Rundle, and I was also an instructor at the physics department. And that's when I learned about peer instruction for the first time. So my question is, we have been using peer instruction here with a number of different features, such as instead of a previous reading, a previous watching some video, like the ones Professor Basalo just mentioned that I have on YouTube. And some of my students complain that what I'm really doing is forcing them to spend more time on the content. So that's why I'm having more success. So how do you do to make sure your students do the pre-lecture reading? Do you bribe them somehow?
I mean, there's a couple of things that are important here to do. I mean, I think to have them do the pre-reading, we actually, if you look at our CW SEI website, we have little 1- and 2-page guides on a whole bunch of different things, and there's one on getting your students to do pre-reading, and because so many, with almost everything, we actually studied what worked and why, and so there's a few basic things you need to do. One is, I'll address first the issue of the amount of time. I look at these courses are exposed to require a certain amount of time from students, and so I think you shouldn't be guessing at what's required. You should have have them every week. I mean, we typically have homework. I assume you do too. Yeah. They'll do some, and the last question on the homework is always, how much time did you spend out of class on this course? And you should adjust what you're asking them to do to stay consistent with time, with the normal expectations, okay? And so that means if you want to have them spend a bunch of time on pre-reading, okay, you've got to make them spend somewhat less time on homework. So so that's the first thing, is you should adjust the time and you should monitor the time. But in addition, what that means is you shouldn't have them have to spend a whole lot of time on preparation for class. You should make sure that it's reasonable, quite targeted, and so that they're not, and they're really focused on what they're going to be using fairly immediately, and you should reward them for it. So typically, what we recommend is having a very short, simple online quiz, which, okay, they have to fill out to do, but they get credit for. That's also useful because you can really target the reading. Like you can have some question on, figure 2.1 tells you such and such. That means you can make, that looking at figure 2.1 is really important, and so you can have them do it. But yes, you reward them for it, and you take into account the amount of time. The third feature we found is really critical for having students do the reading and feel that it's valuable consistently is you have to absolutely avoid something that I'm sure you don't do, but we've seen many instructors do, which they come into class and they say, well, you were supposed to do this reading ahead of time, but I know a bunch of you didn't do it, so now I'm going to repeat what was in that reading, of course. Right. And by doing that, you're punishing all the people who did what you wanted them to by wasting their time, rewarding all the people who didn't do what you wanted to. And you do that once, and boy, they won't do the reading, nobody will do the reading again. So that's a really,
hopefully,
that's a really critical mistake to avoid.
Thank you, Professor, and welcome to Brazil.
Okay. Thank you, Sá Martins. Thank you, Professor Wyman, for your answer. So I have questions myself, but since I've tried to be polite, I'll just make the questions of other people. And now, Professor Vera Henriques from São Paulo University. Vera, do you want to make your question, or do you want me to read it for you?
Okay, I shall make my question. We tried an experience at the University of São Paulo and had tremendous opposition from a group of professors. But the question I wanted to ask you is there any difference? Is there any important difference between students, the scientific teaching for students, initial students, and more advanced courses that you mentioned?
The underlying principles are really the same. Okay, so I think if you look at my diagram of expertise and what goes into that design, those principles are the same. But in terms of the details of what you have the students do and the kind of feedback, that's clearly needs to be adjusted. Well, and the motivation aspects, that clearly needs to be adjusted to the students, because there's, things that a third-year physics student will get excited about. The beginning, first-year student who's taking this course because they want to go off to bioengineering, is going to be a very different sort of thing. Similarly, what's challenging for them, the issue of the level of mathematical rigor you would expect. So I think, like I say, I think we have pretty good evidence that the underlying principles are completely consistent, but the implementation you have to make, and the design of activities really needs to be adjusted accordingly. And I emphasize that because I know some people have, and with all of these things, I mean, it's kind of funny that physicists would do this, but it's true that, they'll take some practice and won't think about the underlying principles, and they'll just take it over to this new situation and expect it works just the same. In the same way some of our students, beginning students, will do these crazy things of, conservation of energy worked in this case, so I'll apply it to this other case where, it has nothing to do with conservation, it's a current flow problem or something. And so I do know of people who kind of ran into trouble with advanced courses where they want to give these simple multiple choice clicker questions, was all they had the students do, as opposed to, no, we want them to think about very, more complex things where simple multiple choice clicker questions are not the right idea, that you can still have some clicker questions. In fact, the quantum field theory course has he's developed some really good clicker questions, believe it or not, that generate a whole lot of discussion. But most of the work is more appropriate there to have, for example, worksheets where they're doing calculations, they're justifying, approximations and so on.
Sure. Thank you very much for the wonderful talk.
Okay, thank you, Vera. Thank you, Professor Wyman. So let's move to the next question. The next question I have registered here is from Alexandre Marcelo. Alexandre, do you want me to read it, or do you want to make it yourself? Okay, so then I'll read it. So Alexandre wrote, how a student can try to use this practice method in a university or course that still uses the traditional method. So is there something that the student himself can do about it?
Yeah. So I get this question a lot. I get it a lot, never from instructors. I get it from a lot of students when I give these talks. And the answer, of course, it's challenging, but you really can do these. I mean, in terms of I sort of listed those kinds of decisions. And so, you can think about as a student, you can go through and look at the material, and you can ask yourself, these sort of basic decisions about either problems. For example, you're given problems to do, think about, okay, how would this extend in some different context? How would the similar ideas apply or not apply, and why? And when you come out with answers to the problems, you can go through think about how you can actually test if these things are right. When you're learning something, you can think about, how would I be able to explain this to someone else? It's extremely useful to try and think, how would I explain this physics idea to my 14-year-old sister? And so I can't use a lot of fancy technical words. I have to think how to put it into a different words, but explain those basic concepts. And so there's really a lot of these things where you can sort of make your brain work hard processing these ideas and thinking through them and thinking how they apply, that actually will get you a lot of the benefits. And finally, I want to stress this book, The ABCs of How We Learn. This is written by a cognitive psychologist who kind of goes through basic ideas of learning, but in these 26 chapters, but at the end of each chapter, they talk about how you can apply these ideas to your own learning. And so that will have a lot of other suggestions beyond what I made here.
Okay, thank you, João, for your question. Thank you, Professor Wyman, for your answer. So the next question comes from João Bertolon. João, do you want to make the question yourself?
Yeah, sure. So first of all, thank you very much for, as an undergraduate student, it's such an honor to be here with all you guys. Like, thank you very much. So I was wondering if, when you were talking about brain constraints, those examples you gave, I reminder of something that happened to me when I first got into college, when we had a class just dedicated to a support for our first physics class. And it was pretty nice, but then I came to realize that some people used to, like in high school, they would learn tricky ways, and I don't really know if that's a specific word for that in English, but tricky ways to remember the formulas for problems. And another example is maybe music. Like teachers would use music to make them remember the content of the classes. And I was wondering if you think that would go into those brain constraints, or if you think that's helpful or not. And I do have a second question, if I might. It's kind of
let's
topic, but
leave it for the second round of questions.
Okay.
There's a lot of
Okay,
questions around.
Sorry.
Thank you, João, for your
yeah.
So for simply memorizing information, which is, I'm going to interpret your first question is, so there are various techniques, and actually I should go back to showing my last present, because people have this reference. So there are various techniques for just remembering things, remembering information, and in the book, The ABCs of How We Learn, they go through these various things. Essentially, the underlying principle of them is connecting them up with other things that are in long-term memory and sort of building the connections to neurons there, and so that it's kind of, you can recall them better. And so, yes, that works fine if you just want to recall information. If you want to think like a physicist, though, the information is really not organized as just a bunch of pieces that's separate pieces that's just recalled. It's actually organized in terms of how it's applied to solve problems. And so it's much more effective if you want to remember things, to think about them in the context of how they're going to be used. You know, and so some formula, you want to remember some formula, you really want to think about how and when this formula is used, under what conditions, and why does this formula have these various, you know, why does it have voltage up here and have resistance in the denominator, as to this formula is really describing a process, visualizing what that process is, etc. That's a way that strengthens it still has the same function of connecting that information to, you know, other neurons and building a bunch of neuron links to it. But the links you're building in that case are directly related to how that information actually gets used to solve problems, and therefore is a technique for remembering things better, but it's a more valuable technique than these kind of simple things of mnemonics, of remembering, and in terms of music, or, you know, where you are in a house and something, so in terms of longer term use.
Okay, thank you. Thank you, Alexandre, for your previous question, João, for your present question, and thank you for your comprehension, for waiting for the second round. We have some questions here. Thank you, Professor Wyman, for your answer. So the next question comes from, well, there are many compliments here, complimenting you for the very nice, excellent, wonderful seminar. I'll pass the chat for you afterwards. Felipe Faria wrote, did textbooks also have to be changed to adapt to this method?
Okay, before I get into textbooks, I want to just make the point, or just ask you, do you have an easy way to make my slides available so all these different people can get them?
Yes, sure. We will leave it in, for sure.
Okay. Just before, because some people will start dropping off. So the question of textbooks is a really complicated one. You know, the first point that one has to appreciate is textbooks aren't actually written or at least published to teach people things. Textbooks are written or published to make money for publishers. And what that means, among other things, is that if you sort of look at the whole process and what sells textbooks and hurt sales, they put a great deal more information into the textbook than actually is useful for students, and is actually in many cases detrimental to students. And so, you know, yes, you could make textbooks a lot better, but textbooks are fundamentally only going to be sources of information. They're going to be limited in their effectiveness of how much they can trigger students to do the right kind of thinking and processing, although they could be better than they are now. But they're never going to replace the critical element of good feedback to students to help guide their thinking, I think. And so, you know, some modification textbooks can help, but they'll never come close to the modification of good teaching methods by a good instructor.
Okay, thank you. Thank you, Felipe, for your question. Thank you, Professor Wyman, for your answer. So I have a question now from Ronai Lisboa. Ronai, do you want to make the question yourself, or do you want me to read it? Okay, I'll read it. Ronai wrote, I've been teaching physics subjects for engineering in large classes. At the beginning, between 100 and 150 students per class. The classes were full. From 2014, I started to work with active methodologies. I took courses, created materials, used new technologies, but I came across a problem. The students run away and seem to prefer classic classes. Today, I have small classes of between 30 and 40 students. Any suggestion?
So I'm assuming you mean like 30 or 40 students, that's the students who attend are only at that level. So I'm going to now also refer back to the resources on the CWSEI website, or you could actually even read my book because I talked about this. So in that, this is really talking about this large-scale experiment we did at UBC to change the teaching across the board. And one of the elements that we had to address, and we did address by research, was to look at what would be basically convince the students that this was good for them, and to get their buy-in to the teaching and learning. And so, I'm just going to refer you to what's written there, because we frankly ultimately were quite successful with substantially greater attendance in all those classes at the Stanford physics classes that we've seen. That was the most immediate thing, that all the faculty that we got to switch over how they were teaching, how their attendance doubled in the class. It was almost perfect all the time now, as opposed to 50% or so beforehand. And so I'll just say it is possible to get very good results this way. It does require some thought about the details of what the activities are, what the students have to deliver, how they're rewarded, the incentives provided to them to do it, both in terms of the marks, etc., but also just the incentives in terms of them feeling rewarded, and rewarding experience of learning more. That's ultimately what we saw made the most difference, is students come to class because they feel it's a lot more valuable to them, use of their time. But I'm going to, all the details about how to make that work, I'm going to just leave you to go have to read it, because I've written down everything I have to say on this, and what we found, frankly, just from the research and experiments worked in achieving these. And now, having said that, it's not like your experience is unprecedented. There's just we've encountered other instructors who have either students don't come to class, or they really object to being taught this way. And frankly, it just comes down usually to missing some key, really essential but not so obvious things. Just like in physics, you have to, research tells you things that aren't totally intuitive, and you have to learn that and put it into practice to get things to work out.
Okay, so thank you, Honai. Thank you, Professor Wyman, for your answer. Honai just added here some books like Principles and Practice by Eric Mazur and Matter Interaction by Ruth and Sherwood. Maybe he wanted to mention these books in his question. The next question comes from Roberto Badzinski. Roberto, do you want to make the question yourself? Do you want me to read it? Okay, then I'll read it. It's not always obvious to students that research-based teaching, active learning, will improve their learning. The teacher is not even teaching, is a common, right? Common saying. What do you do to make students realize quickly that they are, in fact, learning more and more deeply this way than in a usual lecture?
So the answer to this is really, this is fundamentally the same as the previous question. So I'll just refer to those resources. The one aspect I will say, I'll just amplify that on that though, is that this structure of having challenging problems that they both challenging but meaningful. You know, you have to put some thought into designing the problems they're going to have to work through so that the students will see that, yeah, this is a, you know, this isn't a meaningless artificial thing. I can see why somebody would really care about this, how I might need to know this in future, you know, work I'm going to be doing. So you design the problems to be meaningful, you design them to be difficult, so that a student look at this initially and say, boy, I don't know how to do this. But that at the end of class, by working through, talking with the you know, fellow students, getting feedback from the instructor, they'll get to the end of the class and say, well, I know how to do something now that I didn't before. I've learned something worthwhile. And so, you know, that goes into the design of the problem, what they do, what kind of feedback they have on that, as well as starting out class by starting out the course by making it clear to them that you're not just doing experiments, they're guinea pigs in your experiment on a different way of teaching, that actually they're being taught this way because there's lots of research showing that they'll learn better from it. So, you know, it's those combinations of factors that we find are really quite, you know, that makes a big impact of getting students much more favorably inclined, not just neutral, but actually very positive about the experience.
Okay, thank you, Roberto, for your question. Professor Wyman, for your answer. Now, I think I almost have exhausted the questions that are present now in the chat, so let me ask you some questions. The first of them, well, my wife is also a physicist, is also a professor in physics, and so we have a special need children that today, I mean, it's not a children anymore. She's 22 years old. She graduated in gastronomy. It's a technical course, but she did. And we were very happy. And one thing that helped a lot, she just came to me, do you recall the Montessori, you know, the first Maria Montessori method classes that she received? And after that, in this, we also have some Center of Science Outreach here, and we use very much this Vygotsky, right, method and this kind of thing. So when she's attending to your question here next to me, and she came to me and remembered me that most of the times this methodology of, you know, the teacher coming around, checking, and even have a more capable partner that can help the group and something like that. So do you think in some ways this method as a whole, I mean, is some kind of evolution of this Montessori and Vygotsky and, you know, this interactive learning thing? Or do you think it's not fair to say that?
I don't think it's fair to say it's evolved out of that. I think it's really I mean, it's kind of like parallel evolution where certain, you know, different types of organisms end up doing similar things to thrive in a given environment. I mean, I think a lot of what was done in so-called discipline-based education research is, you know, starting with physicists, they just started doing experiments on teaching and learning in university courses, and they arrived at, you know, certain things they found worked. And yes, I think so they came to those quite independently. Are they, you know, is that surprising? No, that's completely reasonable because it's all, everybody in some ways is studying different ways the human brain learns. And so, and these fundamental principles apply, same human brain. And so, yeah, so I think it's sort of a parallel evolution as opposed to a progression from the Montessori and Vygotsky.
Okay, thank you very much. I like very much your answer. So let me move to maybe a more Brazilian typical question. So more and more the students are arriving at the university with very, very low background. So we are, I mean, threatened more or less like to teach what they should have learned in high school. So which do you think is the best strategy for the developing country teachers, you know, that are dealing with this kind of problem? We cannot change the government. And I should not say anything about our government because I don't have good things to say, right? And so which is the advice? Which is the best strategy you think we should follow?
We both have problems with our governments. We can sympathize. So this is becoming, you know, more and more of an issue in the U.S. as well. In fact, I think you'll see that it's fairly similar, and frankly, probably for fairly similar reasons. That you know, in the U.S., the level of education that a student gets is mostly determined by how wealthy their school district is. And this is particularly true with regard to physics instruction, because there's a big shortage of good physics teachers. And so they're almost all in wealthy school districts, because if you're a physics teacher, you can be quite selective on where you go. And so, you know, even at Stanford, and my group has been saying this quite a lot, there's a tremendous difference in how much their level of physics preparation, and what we see is with the current physics courses, the ones who come in with weak preparation have very little chance of being successful. And so you have to ask, well, so what do you do about that situation? I think this is something that basically physics departments in the US and likely everywhere are really going to have to confront, because I think the reality is that historically departments are set up to really serve and optimize their education for a very select and frankly educationally privileged group. Now, so what that means is that if you're going to do the best service to society, I think what you have to do is say, well, okay, you know, that's what we were doing, and that was fun, because we could ignore all of these students who come in without very good preparation from high schools. But the reality is that's the students we have. And if we're going to serve society, we have to educate those students, not just focusing on the students that we wish we could get. And, you know, in terms of teaching those students, there's no difference in anything I've said here. It just means you have to adjust the pace and the content to match those students' backgrounds instead of the students' backgrounds who were very well prepared coming in, and so from high schools. And so you can complain about the high schools and figure it's not your problem, or you can figure, well, look, if we're going to be responsible parts of society, if we're going to really justify to the population at large our educational value, we'll just have to be, you know, work to be most educationally effective for all the students, not just the ones we'd like to teach.
Okay, thank you, Professor. A somewhat related question is that, so the students enter, and then you have normally the courses for preparing future teachers and future researchers in physics, right? Yeah. So we are arrived in a situation is that our course is essentially too much to prepare the physics teachers, because they don't know, they have not learned even the physics they needed to learn to be physics teachers in the high school, and we cannot give the correct preparation for the future researchers. So do you think we should really have separate courses for these two different careers, or a unified thing is more effective, with the fact that, I mean, more and more, I mean, it's going to be difficult to separate, I mean, these two kinds of things?
You know, I think, I think you some level of differences in preparation you can cover with effective teaching. The ways I talked about for teaching and the research-based teaching, they are more effective for less prepared. You know, we have data showing that they are more effective for less prepared students. And when those students are mixed in with more prepared students, this teaching method's much more effective than the traditional lecture. On the other hand, no, you can't. You have to be realistic. I mean, we're looking at Stanford at students who come in to Stanford, want to go in engineering, and some of them have had no physics in high school at all because their school didn't ever have anyone who knew physics to teach them. And we have other students who've had 2 years of good physics teaching. And that's, you know, there's just no way you can reasonably throw those students together. So you have to have, you know, if you're going to be effective, one has to have parallel, you know, different sets of courses. I think, you know, one really has to be very thoughtful and sort of thinking about at what level do you have to have separate courses, and at what place can you have courses in which they overlap, and just to have optimum use of resources. That may mean that it's not quite as optimum for the best prepared ones who are going into research, and so you have to make some compromises. But you know, that's a question one just has to face, and the question department has to face is, how are we going to distribute our resources to get the most optimum outcomes, and what do we care about the most in those outcomes? But I think your point is well taken, that it's simply not realistic to think you can throw these very different levels of preparation and very different career paths into the same courses and have them all, you know, be highly successful and educated to what you care about.
Okay, thank you very much. We have some questions, like 5 or 6 questions more. Can we go ahead with this 5 or 6 questions, Professor?
Sure.
Okay, thank you very much. So first, a comment by Mateus Pereira Lobo. He wrote a scientific article.
Actually, I'm going to interrupt here. I need to look at my calendar and okay, yes, my schedule's free now. Okay, go ahead.
Okay, thank you very much. So Mateus Pereira Lobo wrote, scientific articles should change on how they are written as well, with more transparency, being more concise, and with less unnecessary distractions. Just like white papers, the open science movement goes in this direction of transparency. I think it's just a comment. But then Eduardo Santos has a question: how to use active methodologies in an educational market that has entrance exams as a parameter?
Yeah, so that's a challenging issue, because, you know, what I would argue is there's nothing fundamentally wrong with entrance exams in principle. In practice, there's a lot wrong with them, because and you know, if you study these, and this is something my group has done along with others, is that what those entrance exams test are not really what you care about the students to be good at, and they have very little predictive value. And this goes back to when I was talking about the students coming into my physics lab. You know, they did great on all these exams, but that didn't mean they could do physics at all. And so you first have to recognize how meaningless these exams are. And one way to think about how meaningless they are is to think about, I always compare them with, okay, what do physicists, or, you know, whatever you're testing on, what do they do in authentic problem solving versus what is happening on those entrance exams. And so if you kind of look at all those kind of decisions that you need to solve a real physics problem compared to what the decisions you need to do well on an entrance exam, you can see how really badly aligned they are. And, and to give you one very specific example, we're studying a lot about expertise. One of the most important aspects of expertise, and something that all experts do very, very early in the process, is decide what information do they need to solve this problem, and then how can they go about getting that information, whether it's looking it up, talking. Most often it's looking to decide who to talk to get that, etc. And then that guides how they solve the problem. So when you essentially lock these students into a room, no access to no other information, and tell them to solve a problem, that's nothing like the way that actual experts solve problems. And doing well on exams that test the things, it's basically testing almost all in memorized facts and not anything about how the process of doing science, solving problems, using that information. And so, I would say that on the one hand, it's not, in principle, it's not necessary to get rid of exams, but in practice, it's probably is, because those exams are testing such incorrect things, basically, and they're so mean. You're making a selection process on completely meaningless criteria, essentially. And so from that point of view, they're a very bad way to start.
Okay, thank you, Professor Wyman. Let's move to the next question then. Marcos Oliveira. Here in Brazil, many teachers don't have this training, and many others are strongly against new methodologies. Assuming that we must improve the training of teachers to use active methodologies before applying or teaching them, how would you solve this cyclic problem?
It's really a cultural problem. It's the culture of university teaching. And so, if you look at my book, Improving How Universities Teach Science, it's really, it's about the Science Education Initiative, which was an experiment in institutional change. So it was an experiment in accomplishing exactly those things. And what we learned was that help and hindered that. Now, in the model that I did, it's not the only or necessarily the best model, but it was good for an experiment, which was I basically got a big chunk of money, and then I made departments compete for that money, and they could get, and up to $2 million to transform their teaching. And so that put in a big incentive to do this. And then we supported a whole variety of things to basically support their learning it, making it as painless as possible for faculty, and minimize the time and help and so on in learning this way. And I, mostly I'll let you go buy my book and read the details there. But, fundamentally what we showed is it's possible to do this. And yes, there's opposition. It goes very much against people's past experience and culture, but that doesn't mean we showed it's not impossible, but you have to address a bunch of issues. And probably the biggest one, I think, is the incentive system, and underlying that is how universities evaluate and reward teaching. And so the first thing one has to start with basically is evaluating and rewarding teaching based on the use of methods that we have lots of research showing are more effective. And so, you know, I look at this as very much like what happened in medicine a century or two ago, a century and a half ago, where, you know, research showed things like washing your hands between patients dramatically reduced infections. And so that went from 40 years between people demonstrating, you know, a factor of 10 decrease in infections and deaths when doctors did this, and when hospitals actually started putting in place the policies that doctors had to do this and started checking up on them and punishing them as they didn't. You know, we're sort of at that starting point of that with it, you know, university teaching, as you've got to think about what you want to accomplish. How am I going to measure if they're doing it? How am I going to incentivize people to do that?
Okay, thank you, Marcus. Thank you, Professor Wyman, for your answer. I have here two questions that I'll try to put in one row. Let's say so. Reinaldo Luiz Cavasso Filho wrote, I have a question too. What do you think about the importance of experiments in teaching and learning physics? And then Pedro Ferreira, the next question wrote, to what extent can simulations substitute experiments in physics learning? And this has to do with the pandemic situation that so many people now are thinking about changing presential laboratories activities with those remote laboratories. So could you say something about that also?
So my group, particularly Natasha Holmes, which is a postdoc with me, and now she's a faculty member in the Cornell Physics Department, has really sort of been leading the long, you know, looking at the teaching and learning of instructional laboratories. And this is a topic in which people have very strong feelings and very little evidence about. And so we wrote a physics, I mean, we did a bunch of research papers, but we wrote a Physics Today article on this that came out about a year and a half ago that I'd refer people to. But the simple point is, the actual educational goals of instructional labs, particularly like introductory physics labs, they're very vague and ill-defined and different for different people. But when we picked one that was the most common, which was really to support the learning of the physics, we collected data on that first from Stanford and then from a variety of other universities that people collaborated. And with the methods we developed, we were able to show that they provided no benefit to learning at all, with really small, like, you know, we were error bars that were getting down to a fraction of a percent of looking at how well students could do and test the learning on this subject, depending on whether they'd had the lab or hadn't. And so, you know, I from this point of view, my perspective is you really have to think very hard about what it is you expect students to learn from these laboratories, from our thinking about what they do and don't learn and why. And we've written a number of papers on this, looking at sort of the cognitive activities that are involved. I end up thinking that they're pretty worthless, as they're almost always used. And it makes complete sense that they're worthless, that the thinking that you want the students to do, that to think like physicists, that all went into the design of the laboratory activity. That's not, it doesn't go into what the students are actually doing and having to process with those activities. And so if you know, we've then gone on to look at, okay, the traditional goals of labs, they're not serving at all when we collect the data. what are some goals they could be effective at, and we think and have pretty good evidence of is that they can be uniquely effective at teaching people how to make a comparison of models with data. And you think about that's an awful lot of what we do in physics, but it's an awful lot of what one's done in science in general, and it's especially with COVID these days and the medical things, it's a really critical aspect of any basic scientific literacy, is being able to understand what a scientific model is and being able to understand how models can be tested with data, what the uncertainties in those comparisons mean, and how what's needed to make them better. So if you take that as your goal of instructional labs, then my own feeling is that simulations, online computer things, can be just as good and a lot cheaper and easier than actual hands-on labs. Now, to be fair, we don't have data comparing that. And my, close colleague, Natasha Holmes, she doesn't agree with that. She thinks that hands-on things have particular special characteristics that would make them more effective. But like I say, that's just absolutely something that you can test experimentally, and I'm sure that you could do pretty well with simulated labs. Now, I will finally say that with the Fed interactive simulations, which by the way are used quite extensively in Brazil, we do have some data on learning the concepts of electricity through people going through standard kind of lab activities of building and troubleshooting, making sense of simple circuits with real hands-on things versus the corresponding thing with the PhET simulation. And there, the simulation was clearly superior, basically, just because of the capabilities of what students can do with it more and see what's happening more.
Okay, thank you, Reinaldo and Pedro, for your questions. Thank you, Professor Wyman, for your answer. Could you say some words about the low-cost experiments, those that you don't have any accurate measurement or anything, but you take a straw and a piece of paper, and after passing one to the other, just to move to the wall or something like that to test electricity, to talk about concepts? Do you think that low-cost experiments are indeed good for teaching concepts in high school and even in undergraduate schools? Can't answer that. I don't know of any sort of research that's looked at that. And when I try and take a step back and say, well, if I don't know research directly, let me try and think about what sort of cognitive processes would go on in the students' brains as they do those. I can't think of anything that allows me to be very confident at all as to I can say. So I think I'll just say plead ignorance. I just don't have the evidence to make a claim one way or the other. Okay, so Ronai Lisboa, that use PhET, as you said, it's very much used in Brazil. Why do simulations show exact results? Would it be possible to insert noise into the results? I am using this period in this semester in a virtual laboratory for engineering classes. The point is that results are always accurate.
Yeah. So coming back to the tests that I was talking about, I was assuming you'd put noise into the simulation. And in fact, we have some of the PhET we've done some research with that, but that's something that's actually quite easy to do, and there may well be some my hesitation is I'm not sure they've been publicly released, but we do have some in which there is noise, and the instructor can actually adjust the amount of noise in the measurements, which is something that's handy to do instructionally, but you can't do with real equipment very well. So yeah, I mean, there's the most, and this is just what the instructors want to use them for and what's optimum. And so most people want to use it for demonstrating concepts. You don't want noise in there for doing the equivalent to real labs. You do want noise, and like I say, it can and is in some of them. And if you're an instructor and you want that in some particular simulation, you should just send email to PhET and ask them if they have that, because it could well be a capability that they just haven't made public yet, but they can tell you, go look at this website and you'll get the simulation with an adjustable amount of Gaussian noise in it.
Okay, thank you, Ronai, again. Thank you, Professor Wyman, for your answer. So I have a last question here from Vera Henriquez. Carl, if physics is a theory of nature's functioning, how can one learn from simulated reality?
If you were never getting anything but what simulated reality gives you, then I would agree that it's a problem. I think that in the learning of physics, though, we need to, we do and tell students, this is what happens, right? I mean, but let me turn this question around and say, okay, we have all these physicists and we all believe in the Standard Model. And how many people actually, built an accelerator to show that the top quark has this mass, and that's none of us have, right? And so we're taking results that are produced by some machine and we believe those results. And so if all the results you're going to look at are things produced by simulation, then that's clearly, you never learn that way. But that's not how we learn physics. Most physics, we learn not by doing the experiments at all, but by knowing what the experiments produced. And so, so I just turn that around and say, we don't, when we're learning physics, using simulations to look at some relationships or looking at in data analysis and how you do it, that's a completely different thing from saying, no, that's going to be the basis of the physics you learn. Now, I will say that we have some simulations where we have good data that, like the photoelectric effect, our simulation, we have data showing it's vastly more effective than for students learning than either just reading about what the photoelectric results are or actually seeing a lecture demonstration of the photoelectric effect, and just because students can't understand what the right features are. And so, we have this photoelectric effect simulation. The students are it can do crazy things, and we talk to them when we're teaching about, okay, we've got a bunch of these phenomena that are being represented. You can understand here, but of course, this simulation is a model for the actual, real world things. And, here's the textbook explaining what's seen in the real world. And you can see some, except some differences, but you can also see many of these ideas in the simulation. You can understand them better by playing with the simulation to see how they work. And so, at some level, and maybe this is a good stopping point, at some level, almost everything we do in physics is we make models. And so we look at some phenomena that happens in the real world, and we create in our physicists' brains simplified models that have underlying principles that show how these things work, and we then turn that into theories and equations, which are, via Ohm's law, which ignores a whole bunch of messy little things that happen in the real world. And so in this same way, I think you can think of simulations as just helping one develop these simplified mental models, which are fundamental to the way we physicists always think about physics.
Okay, Professor Wyman, thank you very much. We are running over your lunchtime, and it's already, getting, 2 hours. So I would like to thank you really very much for this wonderful 2 hours that we spent learning with you, listen to this excellent talk. And I'm sure that from the chat that I've read and from the faces I see smiling and really delighted with this moment that the Brazilian community had with you. So I would like to thank you very much. And I'll ask everybody then to turn on their microphones and in acknowledgement, clap our hands. We have about 70 people already in the audience, so it's a lot of people. So thank you very much once again.
I can only... It's been a pleasure, and I admire your patience, and I will, right after this, I'll send you my copies of my slides for you to make available to people. So, okay.
Thank you,
Thank
Professor.
you.
Thank you very much once again.